Welcome to today's deep dive. We're tackling maps, all thanks to your pick, Paulina Rowinska's IndieW Mapmatics.
A great choice. Maps might seem straightforward on the surface, but there's a lot more to them than meets the eye, as Rowinska points out.
Exactly.
Mhm.
We've all seen those classic maps, the ones plastered on bedroom walls or even globes.
Right.
But they actually tell different stories about our planet.
Yeah.
It's all a matter of perspective.
It really is. You can't just translate a sphere onto a flat surface without some distortion. Imagine flattening half a tennis ball. You're going to end up with some stretching and warping. And that's not just about how the map looks, it affects how we understand distances, sizes, even the relationships between different parts of the world.
So what you're saying is every flat map is essentially making a choice about what to emphasize and what to downplay.
Precisely.
Right.
And those choices, they have major consequences impacting navigation routes, international relations, how we perceive entire continents.
Okay, that's already making me rethink everything I thought I knew about maps.
It's fascinating stuff.
But before we dive into all that distortion,
Sure.
I'm curious, how do we even get from those basic sketches to the detailed maps we have today? It seems like a huge leap.
It's a question Rowinska tackles head-on, and one of the biggest game changers was something called triangulation, a technique that emerged back in the 16th century.
Triangulation, okay, that's taking me back to math class.
It is math, yeah, but incredibly elegant math. Think about it trying to measure every single distance on a map. Talk about tedious. Triangulation uses angles and trigonometry to calculate those distances, all starting with just one accurately measured baseline.
So one accurate measurement unlocks a chain reaction of distances.
Exactly. It's incredibly powerful. Rowinska details how this method spread through Europe like wildfire. It allowed for surprisingly accurate maps, even before we had fancy tools like GPS.
It's amazing how one idea can revolutionize a whole field. And speaking of revolutions, this quest to map the Earth led to some pretty epic adventures, right?
Yeah.
Rowinska talks about those French scientists who went to the Andes Mountains in the 18th century. Talk about dedication.
It does sound adventurous, but Rowinska doesn't shy away from the very real challenges they faced. Imagine these academics, used to their comfortable studies, dropped into the harsh conditions of the Andes Mountains.
Okay, so let's unpack this. What were they up against?
Well, for starters, they were completely unprepared for the extreme cold. They faced resistance from the local population and had to deal with political turmoil.
Sounds intense.
It was. And their initial estimate, 2 years, way off. Some of them were gone for over a decade. And tragically, some never returned at all.
That's a stark reminder that map making isn't just about lines on paper. It's a human endeavor with real risks. Their dedication makes you appreciate those maps even more.
It does, and despite all those hurdles, their mission was a success. Those incredibly precise measurements, they were crucial for understanding the Earth's actual size and shape.
Talk about a legacy. It really makes you think about all the unsung heroes behind the maps we take for granted.
It really does. And speaking of brilliant minds, there's one we can't ignore, Carl Friedrich Gauss.
Right. Rowinska talks about how Gauss wasn't just a math whiz. He got his hands dirty with geodetic surveys.
He did.
It's like those real-world challenges fueled his theoretical breakthroughs.
Exactly. While some might have seen fieldwork as a distraction, Gauss saw inspiration. He was fascinated by the challenge of projecting a curved surface, like our planet, onto a flat map.
Which is where his concept of curvature comes into play.
Exactly.
I love how Rowinska uses the example of a banana in her book
It's a great analogy.
to show how a surface can curve in different ways.
It really helps visualize it. It's essentially how mathematicians describe the behavior of a surface at a specific point. So a flat piece of paper has zero curvature, but a curved surface, like that banana or even an egg, has different curvatures depending on how you look at it.
And this is where Gauss made his mark. He found a way to describe the curvature of any point on a surface with one number. It's like he condensed all the different ways a surface can curve at a point into this one neat value.
Exactly. He called it Gaussian curvature. It's a fundamental concept in differential geometry, but it sounds a lot more complicated than it is. It's really about understanding curves, surfaces, shapes, and it's directly related to why we have so many different map projections today.
Okay, I'm starting to see the connection here.
Yeah.
So understanding curvature is essential for accurately translating our spherical Earth onto a flat map.
Precisely. It explains why different projections create different types of distortions. And it also highlights why there's no single perfect map. Every projection involves making choices, trade-offs.
So it's not about finding the right map. It's about choosing the most appropriate one for a specific purpose.
Exactly.
And this brings us back to those great circles. Rowinska talks about those shortest paths between 2 points on a globe.
Right, like think about flying from, say, London to Tokyo. The shortest route isn't a straight line on your typical flat map. It actually curves because it's following the Earth's curvature.
Which explains why those flight paths on those flight tracker apps always look curved. I always thought they were taking the scenic route, but it's actually about efficiency.
Exactly. Airlines are very aware of this. Flying closer to those great circles saves them time and fuel.
So the shape of our planet directly influences air travel routes,
It does.
which then influences where airports get built. It's like this chain reaction of geographical consequences.
It really highlights how interconnected everything is: geography, transportation, economics, even politics.
Rowinska gives that great example of Anchorage, Alaska,
Oh, yes.
during the Cold War because the Soviet Union closed off its airspace.
Right.
Flights between Europe and East Asia had to go over Greenland and Alaska, making Anchorage this unlikely international hub.
It's true. It shows how geopolitics literally reshaped global air travel routes.
When Anchorage became this key refueling stop, it's a real-world example of how maps aren't just about physical reality.
Right.
They reflect political and historical context, too.
Precisely. And this whole idea of maps reflecting more than just the physical. It's crystal clear when you look at the Mercator projection.
Oh, the Mercator projection,
Sure.
the map that's everywhere. Classrooms, textbooks, even our phones. It's like the map, the definitive representation of the world. But Rowinska calls it the Mercator myth. What's the myth and why should we care?
Well, the myth is that the Mercator projection shows the sizes of land masses accurately.
Okay.
It's great for preserving shapes and directions, which is why it's so widely used for navigation.
Right.
But it really distorts sizes, especially as you move away from the equator.
So that whole thing about Greenland looking like it could swallow South America,
Exactly. It's a classic example of Mercator distortion.
it makes Greenland look huge.
Right. And it makes Africa look smaller than it really is.
So how does that impact our understanding of the world?
Well, think about it. If you're constantly looking at a map that inflates the size of certain regions, does that subconsciously affect how you perceive their importance?
That's a really good point.
It's a reminder that every map reflects a perspective, a choice about what to emphasize.
It's like those optical illusions where you can see two different images in the same picture.
Mm-hmm.
So if Mercator isn't the be-all and end-all, what are the alternatives?
Thankfully, there are many. Rowinska walks us through a variety of map projections, each with its own strengths and weaknesses. One example is the Robinson projection.
Okay.
It aims for a more balanced representation of those landmass sizes we were talking about.
So it might not be the best for, like, plotting a ship's course,
Right. It's not ideal for navigation.
but it gives a more accurate view of how the continents are actually distributed.
Exactly. It's all about trade-offs. What's the most important factor for the task at hand? Some maps are great for showing directions, others for comparing areas.
So it's like having a toolbox of maps.
Exactly. You choose the right one for the job. And just like any tool, it's crucial to be aware of its limitations.
Which brings me to a question that's been bugging me. We always talk about maps representing reality. But what happens when reality itself gets a bit fuzzy? Like with that coastline paradox Rowinska talks about, that sounds like something out of a riddle book.
The coastline paradox is a great example of how our intuition about measurement can be challenged. It all comes down to fractals.
Okay, fractals, those things are always so mesmerizing to look at.
Right.
But how do they play into this?
Well, think about measuring the length of a coastline.
Okay.
The length you get actually changes depending on how closely you zoom in.
Wait, so the more accurately you try to measure it.
The longer it gets. Yes.
Yeah.
It's because coastlines have this kind of infinite level of detail. And that's where those mesmerizing fractals come in. Those self-similar patterns that repeat at different scales.
So we're talking about maps, distortion, reality getting a bit bendy.
Exactly. And those intricate fractal patterns aren't just visually stunning, they're all around us. Coastlines, mountains, trees, and they have practical applications too. Have you ever wondered how we create those super realistic landscapes you see in movies and video games?
Oh, you mean like those breathtaking natural environments?
Exactly. Well, it's thanks in part to fractals. Rowinska talks about how those fractal algorithms completely revolutionize computer graphics, allowing for incredibly detailed digital landscapes.
Wow, I had no idea. That's fascinating.
Ah.
So we've gone from using triangles to measure the Earth to using fractals to create entire virtual worlds.
It really shows how these concepts that seem purely theoretical actually shape our everyday experiences in ways we might not even realize.
It really does.
Yeah.
Okay, so we've explored the surface of maps.
Right.
We've gone fractal with coastlines.
Yep.
But now I'm ready to go even deeper.
You mean?
Literally. Into the world beneath our feet.
Yeah.
Tell me about mapping the Earth's interior.
Now we're getting to the heart of the matter, literally. But how do you map something you can't even see? Imagine trying to figure out what's inside a present without unwrapping it.
That's a good analogy.
Instead of ribbons and bows, scientists use seismic waves, those vibrations that travel through the Earth.
So by studying how those waves travel, we can actually get a glimpse of what's happening deep inside the Earth.
Precisely. It's like giving the Earth a giant ultrasound.
I love that. It's incredible how much we can learn about our planet, even without digging into it. Speaking of groundbreaking discoveries, you mentioned Inge Lehmann earlier.
Oh, yes. Inge Lehmann was incredible.
Remind me what her contribution to mapping was again.
Well, she was a Danish scientist, and she actually discovered the Earth's inner core.
Wow. And she did that how?
Using nothing but seismic data and her own brilliant mind.
No way. Just seismic waves. That's remarkable. And this desire to map the unknown, it extends beyond our own planet.
It does.
Rowinska also talks about mapping other planets, right?
Absolutely. It's one of the biggest challenges in planetary science.
Okay, so we've gone from the Earth's core to outer space. This deep dive is taking us everywhere.
And one of the most fascinating examples Rowinska highlights is the InSight mission to Mars. They sent a single seismometer on that lander to study the Martian interior.
Just one seismometer, that seems almost impossible.
It was a huge feat of engineering, but just by analyzing those subtle Martian tremors, they were able to create a detailed picture of Mars's internal structure.
And they discovered a surprisingly large core.
Exactly.
Which tells us what, exactly?
It helps us understand how rocky planets form, including our own. These maps of Mars aren't just about satisfying our curiosity, they're giving us clues about the early solar system.
It's like each map is a piece of a larger puzzle. It's not just about the where, it's about the how and the why. Okay, so we've talked about mapping the Earth's surface, we've even gone fractal with it, but then Rowinska introduces us to the idea of scales.
Scales are fundamental to how we represent the world on a map.
Okay, when you say scales, you're not talking about fish scales, right?
No, haha, not this time. I'm talking about the level of detail. Think about those detailed city maps you might use to navigate versus a world map.
Oh, right.
They both show the same thing, our planet, but the level of detail is vastly different.
It's like zooming in and out on Google Maps. You see different things depending on how close up or far away you are.
Precisely. Rowinska compares it to a dollhouse. The dollhouse is a representation of a real house, but simplified, with less detail.
It's a great analogy.
A small-scale map shows a larger area, but with less detail, just like the dollhouse. And a large-scale map shows a smaller area, but with way more detail.
Okay, that makes sense. So choosing the right scale isn't just about showing more or less land.
Right.
It's about deciding what level of detail is most important for what you're trying to show.
Exactly. And that choice can drastically change how we understand and use a map. Remember the coastline paradox we talked about earlier?
How can I forget? It still feels like a magic trick.
Well, the scale you use to measure that coastline directly affects the length you end up with. The smaller your measuring stick, the more detail you pick up, and the longer that coastline seems to get.
It's amazing to me how something that seems as simple as measuring a coastline can be so complex.
It's one of those things that makes maps so fascinating. There's always more to discover, more layers to uncover, and Rowinska does a fantastic job of guiding us through those complexities.
It really makes you appreciate that maps aren't just about getting from point A to point B.
They're not just navigational tools.
They're a reflection of how we understand the world, shaped by science, history, and even a bit of artistry.
Speaking of art, have you ever looked at a London tube map
Oh, yeah.
and wondered why the distances seem so off?
Now that you mention it, those maps always feel more like a schematic than an accurate representation of the city.
They are, and that's because they're a great example of topological maps.
Topological maps. Okay, I need to hear more about this.
Imagine you're designing a map specifically for a subway system. What's the most important thing you need to communicate to the user?
I guess, like which stations to go to and in what order.
Exactly. You want to show the connections clearly, even if the distances aren't perfectly to scale. That's what a topological map does.
So it's less about geographical accuracy and more about clarity.
Exactly. It's like a diagram, showing the relationships between things rather than their exact positions.
Okay, so it's about efficiency.
And this is not a new idea either.
It's not.
Rowinska points out that Native Americans were already creating these topological maps long before Europeans arrived in North America.
Really? What kind of topological maps were they making?
One amazing example is the Catawba deerskin map from the early 18th century. It's literally drawn on deerskin, and it depicts the relationships between different Native American tribes and their territories.
So they were mapping out their social and political landscape.
Exactly. It shows that maps can represent so much more than just physical geography.
That's fascinating. It makes you realize that those early topological maps, which some Europeans dismissed as primitive, were actually way ahead of their time.
They really were. They embodied design principles that we still use in maps today. And speaking of good design principles, let's talk about the importance of legibility, especially in city maps.
Legibility.
Yeah, when you're navigating a city on foot, you need a map that's clear, easy to understand.
Right, because when I'm walking around a new city, I need to know how far things are from each other,
Yeah.
not just their relative positions.
Exactly. And that's where legibility comes in.
So what makes a map legible?
Well, it should be easy to understand at a glance, with clear symbols, easy to read fonts, and a clear hierarchy of information. What's the most important information for the user? Make that stand out.
It sounds like the map version of good user experience design.
Precisely. A good example is the Legible London project.
Oh yeah, I've heard of that.
It was a huge success. Before this project, navigating London on foot was a nightmare because each borough had its own signage system.
Oh no, talk about confusing.
Right. Legible London brought order to the chaos by creating a unified pedestrian-friendly signage system.
And it made it much easier to explore this city.
Exactly. It's a great example of how a well-designed map can actually change how people experience a city.
It's like suddenly walking becomes a more enjoyable experience. You're not constantly lost and frustrated, so you're more likely to ditch the car and explore on foot.
Exactly. And just like there are different ways to design a map, there are also different ways to define and measure distance.
Okay, I have a feeling this is where the math comes back in.
It's not as intimidating as it sounds.
Famous last words.
When we talk about distance, we usually mean the shortest straight line between 2 points, right? We call that Euclidean distance.
Right, that makes sense.
But there are other ways to define distance. Imagine you're a taxi driver
Okay.
navigating a city grid. You can't just cut through buildings, right? You have to follow the streets. And that's called the Manhattan distance or taxicab distance.
So the shortest route might actually be longer if you have to stick to the grid.
Exactly. It's like that classic joke, a hotel advertises as being just 10 blocks from the beach, but they measured those blocks as the crow flies.
Oh no. That's brutal. They didn't account for the actual streets.
It's a classic bait and switch. But it highlights why understanding the context of a map and the type of distance being represented is so important.
It makes a huge difference. Okay, so we've talked about different types of maps, but there's one type we haven't talked about yet.
And what's that?
The ones we carry around in our heads. I'm talking about those mental maps or cognitive maps that Rowinska talks about.
Ah, yes, our internal navigation systems. We all have them. It's how we navigate our surroundings, how we remember locations, how we can plan routes without constantly checking Google Maps.
So it's like having an internal GPS.
Exactly. And you know what's even cooler? Neuroscientists have actually found specialized cells in the brain that help create and maintain these cognitive maps.
No way. Seriously. There are brain cells dedicated to our sense of direction.
There are. Rowinska talks about place cells that fire when we're in a specific location, and grid cells that fire in a grid-like pattern when we move through space.
That's amazing. So our brains are constantly creating these intricate mental maps in the background without us even realizing it, and that's how we make sense of the world around us.
It's like our brains are hardwired for mapping, and these cognitive maps aren't just cold, hard data.
What else influences them?
Well, they're shaped by our experiences, our memories, emotions, even our social connections.
So you're saying our mental maps are as unique as we are?
Absolutely. Your mental map of your hometown is going to be different from mine.
Because we've had different experiences in that same physical space.
Exactly. And just like those physical maps we were talking about, which can be influenced by things like politics, our cognitive maps can be shaped by factors we might not even realize.
Like what?
Well, our gender, our mode of transportation, even our cultural background.
Interesting. So, for example, if I walk everywhere, I'm going to have a different mental map of my city than someone who mostly drives.
Exactly. Rowinska points out that people who walk tend to develop richer, more detailed cognitive maps because they're more engaged with their surroundings.
Because they're paying more attention to the little details.
Right. They're noticing the shortcuts, those hidden alleys, the things you might miss if you're always behind the wheel.
That's a good point. It's like the difference between knowing a place like the back of your hand and just having a general sense of where things are. Okay, time for another history lesson. Rowinska takes us to 18th century Königsberg,
Ah, yes. Königsberg.
a city famous for a bridge puzzle.
Famous for its 7 bridges and the puzzle they inspired.
So what was this puzzle?
The challenge was this. Could you find a route through the city that would cross each of the 7 bridges exactly once?
It seems pretty straightforward. I mean, couldn't you just try out different routes until you find one that works?
That's what people thought. But this deceptively simple puzzle captivated a brilliant Swiss mathematician, Leonhard Euler.
What did Euler discover?
Well, he realized the key wasn't the actual physical layout of the bridges.
Yeah.
It was the underlying connections they created. So instead of seeing a city with bridges, he saw a network. Land masses became points, bridges became lines connecting those points.
It's like he was creating a topological map of the bridges.
Exactly. And this, believe it or not, laid the foundation for a whole new branch of mathematics.
Which is?
Graph theory.
Graph theory.
It sounds intimidating, but it's really about understanding networks, relationships, connections, and it's become an essential tool in so many fields.
Wow, so this simple bridge puzzle led to a whole new branch of math. That's amazing. It makes you wonder what other hidden connections are waiting to be discovered in the most ordinary things. Speaking of connections, I'm curious how this graph theory is actually used in the real world.
Well, one classic example is the traveling salesperson problem.
Okay, what is the traveling salesperson problem?
Imagine you're a salesperson, right? And you need to visit multiple cities and then return home. The challenge is to find the shortest possible route that covers all the cities.
That sounds like a logistical nightmare, especially if you have a lot of cities on your list.
It can be incredibly complex, and it's not just a theoretical problem. It has huge implications for logistics, transportation, even things like DNA sequencing.
So how do you even begin to solve a problem like that?
There are a few different approaches. Sometimes we use algorithms to find the absolute shortest route, but for really complex scenarios, we use heuristics. They're like rules of thumb that help us find good solutions quickly, even if they might not be the absolute shortest route possible.
So it's about finding a balance between accuracy and efficiency.
Exactly. Rowinska gives an example of the nearest neighbor algorithm. Basically, you just go to the nearest unvisited city until you've been to them all.
It sounds so simple when you put it like that.
Right. But it can get really complex really quickly, especially when you have a lot of destinations and factors to consider.
It's amazing how a problem that sounds so theoretical, like a traveling salesperson, actually has so many real-world applications.
Absolutely. It's not just about abstract math. It's about solving practical problems. Rowinska even talks about researchers at Georgia Tech who use these heuristics to help optimize delivery routes for the Meals on Wheels program.
That's amazing.
They're using these complex mathematical concepts to make a tangible difference in people's lives.
I love that. Okay, ready for another mind-bending math concept?
Bring it on.
Rowinska takes us on this colorful detour with something called the four-color theorem.
Ah, yes. The four-color theorem, it's a classic.
What is it?
It states that you can color any map using just 4 colors so that no 2 regions that share a border have the same color.
Okay, I have to admit that sounds kind of fun, like a challenging coloring book.
It is fun, but it also puzzled mathematicians for over a century.
What was so puzzling about it?
They were trying to prove that you never need more than 4 colors, no matter how complex the map, and proving it turned out to be incredibly difficult.
So did they eventually prove it?
They did, but it took a lot of false starts, clever insights, and eventually computers to help crack the code. It was actually one of the first major mathematical theorems to be proven with the help of computers.
Wow. So this seemingly simple coloring problem actually pushed the boundaries of mathematics.
It did. And like so many things map-related, its implications go beyond just coloring. Rowinska makes this fascinating connection to the very real and sometimes controversial world of gerrymandering.
Gerrymandering, you mean manipulated the boundaries of voting districts to give one party an unfair advantage?
Exactly. It's been around for centuries, but it's gotten even more, well, creative with the use of computers and voter data.
So how does this connect to the four-color theorem?
Well, the principles behind it, the ideas about regions and borders and how they relate to each other, can be used to understand and potentially even combat gerrymandering.
Wow. That's fascinating and a little terrifying.
Yeah.
This abstract math problem is connected to real-world issues of fairness and democracy. It really shows how maps and how we choose to draw those lines on a map can have a real impact.
They absolutely can. And this leads us to another area where maps are really important for understanding social issues.
Okay.
Things like inequality.
Right. It's easy to talk about inequality in the abstract,
It is.
but maps make it visible.
They really do. Rowinska talks about school segregation, which is a huge issue in many countries.
Yeah.
Often, those school district boundaries are drawn in ways that just reinforce existing patterns of residential segregation, which then leads to unequal educational opportunities.
It's like those maps that show the racial and economic makeup of neighborhoods.
Right.
They really highlight how segregated so many cities still are. And those divisions are often reflected in our schools.
It's a complex issue, but Rowinska also talks about a project that's using mapping to try and address this.
Oh, really?
It's called the Mapping School Diversity Project.
So they're actually using maps to combat segregation. How does that work?
Essentially, they're using GIS technology to analyze school district boundaries and student demographics. GIS is basically like superpowered digital mapping.
Okay.
It allows them to see the patterns of segregation really clearly and then explore ways to maybe redraw those boundaries to try to create more diverse and equitable schools.
That's really inspiring. It shows how mapping can be used not just to identify a problem, but to actually be part of the solution.
It's a powerful tool for social change.
It really is. Okay, before we get too caught up in the digital age, Rowinska takes us back in time to 19th century London,
Ah, yes.
to a cholera outbreak that was solved by, you guessed it, a map.
This story is a classic example of the power of maps in public health.
Tell me everything. I need to hear this story.
So cholera was ravaging London, and no one could figure out why. This
God.
physician, John Snow, suspected it was linked to the city's water supply.
Makes sense.
So he creates this map, but not just any map. He makes what we now call a dot map, marking the location of each cholera death.
And those dots revealed something interesting.
They did. The dots clustered around a specific water pump on Broad Street.
Oh, wow.
Snow's map was so convincing that the authorities removed the pump handle, and almost immediately the outbreak subsided.
The map literally saved lives.
It did. It was a turning point in the history of public health, epidemiology.
It's amazing to think about. This simple map had such a profound impact.
It really shows how powerful maps can be. And this legacy continues today. Rowinska talks about how modern epidemiology relies heavily on maps to track diseases.
Oh, for sure. So instead of cholera outbreaks, we're tracking things like the flu, or more recently, the spread of COVID-19.
Exactly. And we have so many different kinds of maps we can use now. Dot maps, choropleth maps, flow maps, each one giving us a different perspective.
And it's not just about tracking the disease itself.
Right.
It's about understanding all those other factors, like population density, access to healthcare, all those things that can contribute to the spread.
Precisely. Maps help us see the bigger picture, which then helps us develop more targeted public health interventions.
So it's not just about reacting to outbreaks.
Yeah.
It's about using maps for prevention, too.
Absolutely. Speaking of which, have you ever wondered how the police use maps?
To fight crimes.
Yes.
I'm sure they use maps constantly. But beyond just marking crime scenes, what else can they do?
Well, there's a fascinating technique called geographic profiling.
Geographic profiling. Okay, that sounds kind of intense.
It does, right. But it's actually a simple idea. Criminals, even the clever ones, they often leave behind spatial patterns with their crimes.
So, like if they're robbing banks, they might target banks in a certain area or near certain roads.
Exactly. And geographic profiling uses those patterns to predict where they might live or where their base of operations might be.
It's like using geography to get inside the mind of a criminal.
It's about understanding their spatial behavior. And it's not just theoretical. Rowinska talks about Kim Rossmo. He's a Canadian criminologist who actually developed the first geographic profiling software in the 1990s.
Whoa. So now we're talking about algorithms helping catch criminals. This is like something out of a crime drama.
It is. And it's been incredibly effective. One case Rowinska talks about is the chair burglar.
The chair burglar. Okay, what is that?
This burglar, operating in California, would leave a chair outside the homes he was targeting,
A chair. Why?
presumably to use as a lookout.
So he had a calling card. A chair. That's both bizarre and kind of brilliant.
It is strange, but it also created a spatial pattern, and that pattern, when combined with the locations of his other burglaries, allowed investigators to use geographic profiling to zero in on his likely home base, which eventually led to his arrest.
Wow. So even something as random as a chair can reveal important spatial patterns. That's amazing.
It's all about connecting the dots, quite literally. So far, we've explored the depths of the Earth, outer space, we've fought cholera and even caught criminals, all with the help of maps.
It's incredible. It really highlights how versatile these tools are.
And our journey isn't over yet. Rowinska takes us on one last adventure, to the bottom of the ocean.
Mapping the ocean floor. Now that's a challenge. It's not like you can just send a surveyor down there with a tape measure.
It's one of the most challenging mapping endeavors. We're talking about a vast, dark, and largely unexplored part of our planet.
So how do you even begin to map something so inaccessible?
Sound. We map the ocean floor using sonar, which relies on sound waves to create images.
So instead of shining a light on something, we're using sound.
Exactly. It's like we're listening to the ocean floor to understand its shape and features.
That's amazing. And how has that technology evolved over time?
It's come a long way. We've gone from these early single beam sonars, which were like using a single pixel camera, to these modern multi-beam sonars that create these incredibly detailed 3D maps of the seafloor. It's amazing the level of detail we can see now.
It's like the difference between like a flip phone camera and the latest smartphone camera.
Exactly, and it's not just about pretty pictures. This technology has completely revolutionized how we understand the ocean. We're discovering underwater mountains, canyons, even hydrothermal vents teeming with life.
It's incredible to think that we're still making such significant discoveries about our own planet.
It is, and these discoveries have huge implications for navigation, resource exploration, environmental monitoring, even climate change research. Rowinska highlights this project, the Seabed 2030 project, which is an incredible effort to map the entire ocean floor by the year 2030.
Wow, the entire ocean floor. That's ambitious. Why is this such a priority?
It's about understanding our planet. The ocean plays such a vital role in regulating our climate, providing resources.
And yet we know so little about it.
Exactly. Mapping it is essential for addressing some of the most pressing challenges facing humanity.
And we're using maps to do it. It's incredible. So we've explored the Earth from its core to the depths of the ocean. But maps can also help us understand our history, right?
Absolutely. Maps are like time machines. They can transport us to different eras and cultures. And one of the things I love about Rowinska's book is how she brings these historical maps to life.
Yeah, she has a knack for storytelling.
She really does. Like when she talks about the Hereford Mappamundi.
Okay, the Hereford Mappamundi, refresh my memory on that one. What's so special about it?
It's this massive map created way back in the 1300s. It shows the world as it was understood in medieval Europe.
So it's more than just a map. It's a window into a different worldview.
Exactly. And it's not just about the geography. It's filled with these incredible illustrations, mythical creatures, biblical scenes, all these things that were important to the people who made it.
It's like a snapshot of their imagination, their fears, their beliefs. It's fascinating to think that something as simple as a map can tell us so much about a culture so different from our own.
It really can. And it's a reminder that maps aren't just objective representations of the world.
They're also products of their time and place.
Exactly. They reflect the knowledge, the biases, the worldviews of the people who created them.
It's like that saying, history is written by the victors.
It's true. And in a way, the same can be said for maps.
So how do we navigate this then? I mean, if maps are inherently subjective, how do we know what to trust?
That's a great question, and it's one that Rowinska encourages us to ask. It's not about blindly accepting maps as these neutral, objective tools. We should approach them with a critical eye.
To question what we see.
Exactly.
Yeah.
To consider who created the map, what their purpose was, what information might be missing or distorted. It's about being map literate.
Map literacy, I love that. It's like we need to learn how to read a map just like we learn how to read a book.
Exactly. And just like with books, the more maps you encounter from different times, different cultures, the better equipped you are to navigate the complexities and appreciate the power of these fascinating tools.
Well said.
It's true, mapping the ocean floor is a huge undertaking, but it's not impossible. We've come a long way in our ability to map this underwater world.
Okay, so walk me through it. How do we map something we can't even see?
It all starts with sound. We use sonar, which relies on sound waves to create images of what's down there.
So we're basically listening to the ocean floor to understand its shape and features.
Precisely. It's like shining a flashlight into a dark room, but instead of light, we're using sound to reveal the hidden landscape.
It's a great analogy. And like any technology, I'm guessing sonar has evolved over time.
Oh, absolutely. Those early sonar systems were pretty basic. It was like trying to create a detailed picture with just a handful of pixels.
Okay, so kind of blurry.
Very blurry. But today, we have these incredible multi-beam sonars that produce incredibly detailed 3D maps of the seafloor. It's amazing the level of detail we can see now.
It's incredible how far we've come. So what are we learning from these high-tech sonar maps?
So much. We're discovering underwater mountains, vast canyons, even those hydrothermal vents teeming with life that we never knew existed before.
It's mind-boggling to think there's still so much to discover right here on our own planet.
It really is. And these discoveries aren't just about satisfying our curiosity. They have huge practical implications for everything from navigation and resource exploration to environmental monitoring and climate change research.
It's a good reminder that we're still learning, still exploring.
Absolutely. And Rowinska highlights a really ambitious effort, the Seabed 2030 project.
Okay, Seabed 2030, what is that?
It's an international effort to map the entire ocean floor by the year 2030.
Wow, the entire ocean floor. That is ambitious.
It's a huge undertaking, but it highlights how crucial it is that we understand this part of our planet. The ocean plays such a vital role in regulating our climate, providing food and resources, supporting such a diverse array of life.
And yet we know so little about it, relatively speaking.
Exactly. Mapping the ocean floor is essential if we're going to address some of the biggest challenges facing humanity.
It's incredible to think about maps. These tools we often take for granted are at the forefront of scientific discovery, global efforts to protect our planet.
They really are. And speaking of groundbreaking discoveries, Rowinska tells a fascinating story about Marie Tharp.
Marie Tharp, I'm not familiar with her work.
Oh, she was a true pioneer. A cartographer who created the first comprehensive map of the Atlantic Ocean floor back in the 1950s. It was a time when women in science faced immense challenges, and the technology was still pretty basic, but she persevered.
That's amazing. What did her maps reveal?
Her maps revealed this incredible feature, the Mid-Atlantic Ridge. It's this vast underwater mountain range that runs right down the center of the Atlantic Ocean.
Whoa.
This discovery provided crucial evidence for the theory of plate tectonics, which completely changed our understanding of how Earth's continents move and interact.
A map helped prove that continents drift.
That's incredible.
It really highlights how mapping isn't just about documenting what we already know. It's about challenging our assumptions and revealing the hidden workings of our world. It's a good reminder to always keep an open mind, to never stop questioning and exploring. Speaking of exploring, Rowinska takes us from the ocean depths to the skies with the story of Air France Flight 447. That plane tragically crashed into the Atlantic Ocean back in 2009.
That was a tragedy.
And the search for that plane, as Rowinska describes it, sounds incredibly challenging.
It was a massive undertaking. It took years of searching and involved international cooperation, cutting-edge technology, and a good dose of ingenuity.
What were some of the biggest challenges they faced?
Well, the ocean is vast, and the debris field was spread out over a huge area. Plus, the ocean floor in that region is incredibly deep and rugged, which made it even harder for the search teams.
So how did they eventually find the wreckage?
Rowinska highlights the role of autonomous underwater vehicles, or AUVs, in the search.
Okay, AUVs, those are like underwater drones.
Exactly. They're essentially unmanned submarines that can be programmed to follow a specific search pattern and scan the ocean floor using sonar and other sensors.
So they were able to cover a lot more ground, literally, than human divers could.
Exactly, and that proved to be crucial in this case. The AUVs were able to operate in those deep, treacherous waters and eventually located the wreckage of Air France Flight 447.
That's incredible.
Yeah.
It's amazing to think that we have the technology to do that, to find a plane that's been lost at sea for years.
It's a testament to human ingenuity and our determination to solve mysteries, even in the most challenging environments.
It makes you realize that maps aren't just static things, lines on paper. They're constantly evolving as we develop new technologies and find new ways to explore and understand our world.
Exactly. And just like maps have evolved, so too has the way we create them. Rowinska talks about the rise of citizen science and how it's changing the face of cartography.
Citizen science, what exactly is that?
Well, it basically involves everyday people, not just scientists and professionals, contributing to scientific research.
Hmm.
In the context of mapping, it could involve things like people using their smartphones to collect data about their local environment, or volunteering to help verify satellite imagery.
So it's like crowdsourcing scientific discovery.
Exactly. And it's having a huge impact. One example Rowinska gives is OpenStreetMap, which is this incredible project to create a free and open map of the entire world.
Wait, a free and open map of the world?
Yeah.
That anyone can contribute to? That's incredible. How does it even work?
Well, it's built on the idea of collaboration. People from all over the world contribute to the map, adding information about roads, buildings, points of interest, you name it.
Sounds like the Wikipedia of maps.
It kind of is, and it's being used for all sorts of amazing things, from disaster relief efforts where up-to-date maps are essential, to urban planning and environmental monitoring. It's a great example of how technology and collective effort can make a real difference.
It's really inspiring. It makes you realize that we all have the potential to be explorers and map makers in our own right. Well, this has been an incredible deep dive. We've explored the Earth from its core to the depths of the ocean. We've ventured out to other planets, and we've even gone back in time with historical maps.
It's amazing to think that all of this and more is contained within those seemingly simple lines and symbols we call maps.
It's a good reminder that maps are more than just tools for navigation. They're powerful tools for understanding our world, for telling stories, for inspiring wonder, and for sparking our curiosity.
They're a reflection of who we are, where we've been, and where we might go next.
Well said. And on that note, we'll wrap up this deep dive. Until next time, keep exploring.